So in the last session, we talked about sending messages from the producer to the Kafka cluster. We had our producer, and inside that we had Avro serializer. Using Avro serializer, we send the messages to Kafka. And we had our schema registry up and running in some port there. Usually the schema registry will be highly available. That's how it has to be maintained. If a schema registry goes down, some other schema registry should be available. And we had our e-commerce logs. So we'll see how the consumer works. So consumer is nothing but our Spark streaming. So consumer is embedded there, Kafka consumer, which in turn uses Avro deserializer. And finally it will give batches of data. So it will give batches of data. And this batches of data will be processed by our logic. Whatever logic we write, so you can do any kind of aggregations there. And we have already seen in the demo what aggregations we are doing. I will just explain all those aggregations. Now earlier what I was doing here is, this is our Spark core, where we get the batches of data and we will start processing this. Earlier we know that we have a zookeeper here. Our Kafka depends on zookeeper. Schema registry also is used for high availability. We also use zookeeper, but in this I am not showing the zookeeper, high availability of the schema registry, but it has to be done. Now we have our zookeeper. So earlier that I will show the offset management. So here offset I was writing to, after processing the data, I was writing the offset to zookeeper. I have slightly made the changes now. Probably the code that you people have in the image, it is where offset is being committed to zookeeper. I have recently made the changes, so I have also written the code to save data and offset to Cassandra database. So recently I have made the changes, but both I will share this code, but this already code should exist with you. Now let's see how the streaming application works. We also already know how the concept of streaming application is. So let's see the code here. So all the code related to streaming application, streaming Spark streaming is in the streaming package. So there you will see log analyzer Kafka streaming, and one more is log analyzer Avro Kafka streaming. So again This was done earlier. Avro was done recently. You should also people should have this Avro one. So here we are getting some configurations parameter from from the properties file. Certain things we need like Cassandra database name. What is the Cassandra database name? So that in Cassandra we call it as a key space. What is the Kafka offset table? Where we want to save the offset. This piece of code will not be there. In your case, these changes you have to make. I will send these changes. Similarly, I have a lookup file. So I will explain this what is lookup file. Then we need to have the topic. We need to also get the batch interval. So everything, most of the things we are getting from the configuration file here. So as usual, we are creating Spark conf object and we are setting some parameters here. So after that, we are creating our Spark context object from the conf object. And just like we used to create a Spark context, then we used to create a SQL context. For streaming application, we have to create a streaming context. So that's what we are doing. We are creating a streaming context from our Spark context, and along with that we also need to specify batch interval. As I said, every batch interval our we will be collecting the accumulating the data, and once the batch interval is expires, all those data will be processed. So it will be something like this. So here also the DAG will be created, everything will happen. So you have your executor. The architecture still remains the same. You will have the driver here, you will have your executor here, you will have your executor here, you will have your executor here. So let's say your task is running here to task 3. So they are getting the data from partitions, from Kafka partitions. So you this is our RDD. It will give out partition 1, partition 2, partition 3. Every batch interval will get one such RDD. Every batch interval, and it will be processed. So the processing DAG is prepared here. So we know that the stages are created here and the tasks are created here. So we have the DAG in which we have stage, tasks. So every batch interval, this DAG will be scheduled. This DAG will be scheduled. So it is like saying you are running jobs every batch interval. Every batch interval, one job will be scheduled. A DAG is nothing but one job. So it will process the data, whatever is available for that one batch interval, Then again after 5 seconds, again next DAG will be, it will be the same DAG. It will be scheduled again and again every batch interval, and whatever data we have for every batch interval, that will be processed. So you can think of batch interval as you have two perspectives for your batch interval now. One is that every batch interval the data will be collected and accumulated. Every batch interval the job will be, or the DAG will be scheduled. So that's how we have to keep in mind about the batch interval. So I hope the how internally things works is clear. So here is our batch interval. So we create a streaming context with that batch interval. Now we are using a broadcast. So if you remember, we talked about the broadcast. Broadcast is all about sending, if you want to send something from your driver to your executor. Now why do we need a broadcast here? So the reason is the way I am generating the log. The way I'm generating the logs is using some files or some IP address to country code mapping. If you see here, I think I had showed this. So using this, I said that I'm generating IP address. So this will be first two octets of our IP address. Next two octets I'm generating randomly. So that's how we get the IP address in our log simulator. Now when I receive the IP address on the consumer side, when the consumer consumes the whole message, the message also has the IP address. From that message, I will get the first two octets. From that IP address, I will get the first two octets, and using that, I will get the country code name, so that we can do from which country how many visits are happening. So that for that sake we are using this file, and this file will be broadcasted. I mean to say, will just like we used to do with the customer data. We read the customer data, transform into a hash map, wrap it inside the broadcast object, and send it to every executor. Because our executor will be getting all the messages, and your message has an IP address as well. So here we'll be getting the messages. So the message will have IP address, timestamp, all these things will be there for every message. Here also you will have IP address, timestamp, and URL, so many things. Now how do we get the name of the country? How do we get the country code name? So these were generated based on that file. We will read that file in our driver. Same like broadcasting. So all class will read this file and create a hash map, where we'll say 1.1.2 is some China, 1.6 is Japan, 1.5 is India, and so on. So we'll create a hash map, and this hash map will be wrapped inside a broadcast object, and that broadcast object will be sent to every executor wherever we are receiving our continuous stream of data. So that's the reason we are using a broadcast here, to get the country name from the IP address. So I hope that was clear. So we are, if you see, this is our lookup file. That lookup file is nothing but our this lookup file is nothing but our all class.txt file. We can see it in the in this configuration also. So this configuration, if you see, it is nothing but all class.txt. So once we read that file, as I said, if anything that is associated with RDD or data frame will be evaluated in the executor, anything else will be evaluated in the driver. Now this is a simple Scala program, hence it will be evaluated in the driver. So we are normal the way we used to create a country code map. So we read the file. We are having our mutable hash map. We read the file as usual, get all the lines, loop through the lines, get line, split it by space because IP address and country code are split by space, as we can see here. It is separated by space. So array, when we do a split, we know that it returns an array of zeroth element will be the IP address octet, array of first element will be the country code. So that's what we are getting here. First element of the array we are giving the name as IP octets. Second element of the array we are giving the name as country code. Now that's what we put in our hash map. IP octets will be the key, country code will be the value, and finally we are returning our country code. And we return the country code hash map from this, and everything is broadcasted. I mean, as you can see here, we are broadcasting that object. So we have created a broadcast object. So this is ready now. I mean, if we don't create a broadcast object, we cannot access that hash map in the executor. Next, what we have? Next is all our consumer configurations. As we said, we need to specify the bootstrap server. We need to specify group ID also. I said is a mandatory parameter. That's how you distinguish between two applications, two streaming or consumer applications. Group ID is the unique ID for each streaming application, or you can say consumer application. Then we have our key deserializer and our value deserializer. And if you are this auto reset is as of now not required. So this is one more mandatory parameter if we are using Avro serializer and deserializer. We need to specify the schema registry. So these are all our consumer configurations. Now using this consumer configuration, we are trying to read the data from, okay, I mean to say uh, the Kafka here. So you people might be having this piece of code. I will showcase both. I will showcase both. I'll comment this. something is wrong. New arguments for create direct stream. String object string decoder. Wrong here. Anyway, I think some changes I have to make here, but I will try to explain it with the. It should work for your Zookeeper. Let me showcase with the Cassandra here. So very first thing what we have to do is, as our streaming application starts, we have Kafka, we have our Spark, and we have our Cassandra. So in Cassandra we have a Kafka offset table. We have Kafka offset table. So where the table looks like it has columns called this has column called partition and offset. So these two are the initially we'll say partition 0, partition 1. Let's say we have three partitions. Offset is set to 0 here. Now as soon as you start the Spark streaming application, as soon as you start the streaming application, it will go and fetch get offset, or we have a method called read offset. read offset. When this is called only during start and restart of Spark streaming. So the read offset method is called only during start and restart of a Spark streaming. Every time you won't contact the offset table in your Cassandra, because once you know that, you will be maintaining the latest offset in your Spark streaming itself. This offset management, I think I have already said that the offset management is only required when you start the application or restart the application in case of error handling. Otherwise, it will maintain its own copy of the latest offset that it has read. So first it will read the offset from here. It will see that for partition 0, partition 1, partition 3, the offsets are, I mean, I don't think so anything will be here. Nothing will be here actually. We will just be creating a table. Actually, nothing will be there in this table. It will be empty. Because how do we know how much partitions we have to create? We would not be knowing how many partition exist in the Kafka. So initially it will be empty. Initially it will be empty. So Spark streaming will, as soon as you start the Spark streaming application, first it will try to read the offset from this table. Now this table content, it returns empty. If it is empty, means we don't know from which offset we have to read from. We don't know which offset we have to read from. So to handle that, so we have a configuration called auto reset, auto offset reset config. What is the use of auto offset reset config? Auto offset reset. So its value could be largest or earliest. Now what do I mean by largest and early? Sorry. So either you can set your auto offset reset to largest, or you can set the auto offset reset to earliest. Now what do I mean by that? So these things are used whenever the Spark is not able to get a valid offset. These configurations are used for whenever the Spark application is not able to get the valid offset. So whenever the very first time when you start your Spark streaming application, you are not getting any valid offset. We are getting an empty here. Nothing is there in this table. So Spark is not getting any valid offset. Since it is not getting any valid offset, it will check for this configuration. In this configuration, either it could be largest or earliest. Now when we say largest, it is the latest offset that Kafka has for that topic. For each partition, whatever is the latest offset the Kafka has, those messages will be read. Those messages will be read. If you set it to earliest, the earliest means, I mean, the earliest offsets that already exist. So we know that there are something other things to be noted here. In server.properties, if you remember when I talked about Kafka, I said that Kafka is a circular message queue. So it will discard the older messages and make room for new messages. So this is how it discards the older messages using log retention Rs. We know that our messages will be appended to a log file, and that log file will be maintained for 1 week. 160 hour comes to 168 hours comes to 1 week. As soon as it gets 1 week old, that file will be deleted. So these two are important for that thing. Log retention Rs, log segment bytes. So what does that mean? So you have your Kafka. This is your broker. I'll say broker one. So your messages will be appended to some dot log file. We know that the messages are appended to some dot log file. So we have some 000. Actually, it is the offset. Actually, it is the offset. Now we also have this, the max size of a log segment file. So this file is called as a log segment file. This file is called as log segment. Now, as soon as this file reaches 1 GB, as soon as it accumulates, as soon as 1 GB of messages are appended to this file will be rolled over, a new file will be created. A new file will be created. A file will be rolled over in the form of, it will be, it will roll over as the latest offset it contains. Let's say here it contains some, uh, some one. So this is the latest offset it contains. So that's how the file will be renamed. After rollover, the file will be renamed with the latest offset it contains. Probably, I mean, somewhere like that. Latest. Again, a new file will be opened. This file gets closed. A new file will be opened again. Now the messages will be sent to that file. So on, the rollover will keep on happening. The latest offset will have something like this. This file contains from this offset till this offset, from this offset to till this offset. So this is all your segment files. For each partition, there will be multiple segment files. These are called as segment. For each partition, we'll have this. Now, as soon as when the Kafka deletes a file, we know that after 168 hours, 168 hours, previous messages are all the messages which are 1 week old will be deleted. How do we decide which messages are 1 week old? With the help of this segment file. If a segment file is 1 week old, it will be deleted from the cluster. It will be deleted from the cluster. So that's how the things gets deleted from Kafka. Now now it may happen that, so after, as soon as it gets 1 GB of data, it gets rolled over and closed, a new file will be opened. As soon as that new file again gets 1 GB of data, Again it will roll over and a new file will be opened. So every time new files will be opened after the messages are filled here, the old files will be closed. So it may happen that it did not get enough messages for 1 month. For 1 month it only got 200 MB of messages. But our deletion time is 168 hours. Our deletion time is 168 hours, but we are receiving only 200 messages, 200 MB of messages per month. So in that case, how this deletion of the segment files will be done? So the way it works here is the files will be deleted only if they are closed. Segment files are deleted only if they are closed. And file gets closed only if it and file gets closed only if there is 1 GB of data, whatever that configuration says. As soon as 1 GB of data, only then it will be. So 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 this open file will never be deleted even if it is 1 week old. This open file will never be deleted. It will be only deleted after it becomes 1 week old. It will be deleted. It becomes 1 week old after it is closed. The time will be checked in that fashion. Once a file gets closed, from that time, as soon as it becomes 1 week old, that file will be deleted. That's how a circular buffer is maintained. Circular buffer is maintained. Now when we say here, so we just took a diversion here because we were talking about largest. So this largest and earliest is nothing but on the open file. Whichever is the largest offset in that open file, from that offset the messages will be read, or whichever is the earliest offset in that open file, from that the messages will be read. So I hope you got the idea of what is the auto offset reset, largest or earliest. So it is only used whenever our Spark streaming is not able to read the data. Okay. Yes. As I was saying, earliest and largest only comes whenever the Spark streaming is not able to find a valid offset. So Spark streaming, whenever we start the streaming application to read the data, the very first time it will not find the valid offset, so you can configure largest or earliest. Here we have earliest, so that we get the data from the starting. We get the data from the starting. So once earliest means it will be from earliest here refer. In our case it means nothing is been there, so from zeroth offset. Whatever is the first message, from that will get start reading the message. So we'll get the message. Every batch interval will be collecting the data. Our batch interval is 5 seconds. Let's say that. So in that 5 seconds, we might have got some 1000 messages. 1000 messages in the form of from partition 0, 3, 3. 33 messages. From partition 1, 334 messages. From partition 2, 333. So we got these many messages from our first batch interval. So as soon as we get that, we commit the offset again. We process the data and we also commit it in this batch. So we'll say partition 0, 333, partition 1, 334, partition 2, 333. So again in the next, we'll again send the request to get in the next batch interval, again we'll be receiving some data. Hello. I think again it's fine now. Still the how about now? I think now it's audible. As I was saying, this is our read offset, and we have to maintain a hash map. I mean, we will get the data from the table and put it in this hash map for use. So our hash map is key is topic and partition, for which topic and which partition, and what is the offset value. That's how the hash map is created. Now we use a Cassandra SQL context. I mean, if you remember, we create a SQL context and we use the data source API to read the data from a table. We know that using Spark SQL, we can read from any structured data source. So Cassandra is also a structured data source, so we can read it from there. And the Cassandra company has written a wrapper on top of the SQL context. So which is nothing but Cassandra SQL context. So we have to create that Cassandra context, which is internally the SQL context itself, and internally it uses the data source API itself and reads the data. So here we are doing select from that table. We are selecting partition offset from table. Table is our Kafka metastore table, and we run that query. We run that query and we get a data frame. We get a data frame here because we know that any query and any SQL query, Spark SQL query, it will return a data frame. So we know that the data frame is nothing but this. If we are checking whether RDD dot probably we could have checked the emptiness there itself. Here itself we could have checked the emptiness. Anyway we are doing the check here. If the offset is empty, return none. If else, return the offset. So what we are doing here, we get that data frame, convert into an RDD. We are doing a collect. Collect, we know that it will return an array. So all your records will be in the form of array. Offset and offset partition number and offset will be your array now. So we take each object and we get the partition and we get the offset. So we already know what is topic. We'll be passing that topic name from our Kafka Spark streaming, and we create our hash map. So this is our I mean to say we get our offset here. We are assigning it to our offset. So if offset is empty, we return none, otherwise we return offset wrapped inside the sum object. So that's how we are reading our offset. So once we read the offset, it is nothing but a hash map. Now our offset is in the form of hash map. So let's say where we are using this. So it returns a hash map. So this hash map could be none object or it could be actual offset. The very first time there will be no offset at all, and we fall in the case none because we have returned none, hence we fall in that none. In that case, here we are establishing the connection with the Kafka. Start from the smallest offset or earliest offset. So this is the only API you have to use. I mean to say this is the API we have to use to connect to Kafka and establishing a streaming connection. Kafka utils dot create a direct stream, and which takes the parameters of our streaming context, which takes all the consumer properties, consumer parameters, and the topic. So here when we use Kafka direct stream, if you don't specify any offset, if you don't specify any offset to the parameter of create a direct stream, it will read the messages based on what is configured as auto offset reset. Auto offset reset. Either it is earliest or largest, so based on that, from that offset it will start reading. In our case it is earliest, so it will be starting from the 0th offset. And continuously you will be receiving the messages. Continuously you will be receiving the messages. Now the case, suppose you get an offset. I mean after this your stream will be continuously receiving the messages and your processing will be done. Once you enter this, once you call this method create direct stream, from here onwards continuously you will be getting the messages, and whatever other piece of code you have written to process, all this processing will be done. All this processing will be done. Now when will this piece of code will be called then? The second case. So it will be called when you restart your application. When something happens to your Spark streaming and then you restart. So in that case, when you restart again, this piece of code will be called read offset. This time it will return a valid offset because we had already saved the offset. I will show how we are saving the offset. We haven't seen that piece of code, but every batch interval we will be saving the offset. Now as soon as you restart your streaming application, again this piece of code will be evaluated. This time it will get some valid offset. This time we'll get some valid offset. So here is a question. The question is how we will restart. When I say restart, you can imagine the application has has been crashed, or you can just use the kill command to kill the Spark stream. You can specify the yarn ID and kill the application. So that's what I am talking. Or it could be because of some bug your system has crashed and then you restart. I mean you redo the Spark submit. You redo the Spark submit. So keeping that in mind, as I was saying, you are reading the offset here. So the next time when you restart, you will get some valid offset. So again, you will establish a connection, create direct stream, but this time we will specify the offset as well. We'll specify the from offset. I hope you got the idea here. The first time, when very first time we start the streaming application, this API will be called, and every time you restart, you will call the create direct stream, and from that we'll be starting reading our offset. So I hope the offset read is clear. Offset management is clear here. We will also see how we are saving the offset. So we saw read offset. Similarly, we have save offset. We know that the offset is inside the message itself. If you remember, I discussed that. So our message itself, the broker writes to the broker generates the offset. We know that broker is the one which generates the offset, and it will embed it inside the message. The offset will be in the message itself. Offset key value. Now, whenever you receive that message, I mean that message is part of now RDD. RDD is collection of these messages. Now RDD itself has the offset. It is not that it is outside the RDD. It is inside the RDD itself. So you need to pass that RDD to this method. Whatever RDD you receive from your Kafka stream, Spark streaming, so you get that RDD. That RDD you pass it. So you convert your RDD as an instance of has offset range. Has offset range. It is the built-in data structure of Kafka has offset range. So you have to convert your RDD as a object of has offset range, and from that you have to get offset ranges. So offset ranges is a collection, I suppose. So from that collection, we are creating our RDD. Because as an RDD, you want to save the things to Cassandra. You cannot just save a array from Spark to Cassandra. Spark can save an RDD to Cassandra. It is best to convert your data or offset details as an RDD and save it into Cassandra. So we take the offset, each offset, we get the offset partition, and offset until offset. So there are two things. There are two things: until offset and from offset. So when Kafka receives messages, sorry, when Spark receives messages, we have our Kafka, we have our Spark. Spark is sending the request. Spark is sending the request saying I want data from sensor topic, zeroth partition, zeroth offset. So it will send messages. All the messages will be there. Along with that, some metadata will be also there. So that metadata will be there saying from offset 0 until offset somewhere around, let's say offset is 99. So it will send the metadata along with the message. So you will also have this 0th offset till 99 offset. So Spark comes to know that it has read up till 99 offset. So that's the reason we are getting our until offset. So it will be in that form. So you will see that offset has, these are all Kafka internal data structures. So you will have from offset. From offset will be the very first time 0, and the until offset is till what offset you have. And then save to Cassandra. Save that RD to the key space to the database this, to the table name Kafka offset, and the columns are partition and offset. So that's how we save the offset. Continuously we will be, so every batch interval, as soon as we receive the data, we we extract the offsets from there for each partition, and that will be returned to the Cassandra database and to the corresponding table. So we can see that save offset. So it depends on where you call your save offset. So here we are reading the messages from Kafka. This piece of code, from here we are reading the messages from Kafka. We haven't processed the messages yet. So before processing, if you save offset, saving offset before processing and saving data, we know that there could be data loss on restarting. This is at most once semantics. So we have already discussed that. So if we call our Kafka streams, whatever is that, I don't know. So we are doing this here. At the last, if you see, we are saving the offset after processing and saving data. So there could be duplicate data on restart. So this is at most once semantics. So we are saving here. If we put this is how we save the offset. As you can see, we after processing the data, then we are saving. So we are achieving at least once semantics. At least once semantics. If we put the same piece of code, if we put this same piece of code, the saving of offset before processing the data, here we are all processing the data and saving the data. If you put this code here, if you put this code here, then we are achieving at most once semantics. Before saving the data, we are saving the offset. So this will be at most once semantics, but both will put in a comment. So this is how you manually handle. You cannot still achieve exactly one semantics, even though our Cassandra database, and even though we are writing the data as well as the offset both to Cassandra, still we cannot achieve exactly one semantics because we are doing multiple aggregation. We are doing multiple aggregation. We are doing we are doing customer sorry visits for each country, visit count, we are doing product count, everything is a different table. Writing to different table is not atomic, is not atomic. So that's how the things work. I hope you got the understanding why it is still not exactly one semantics. Again I will discuss that, but I hope you got to understand how to manage offset here, how the offset management works. Write and store the offset and read the offset every time you restart from the external storage. Now once you have read the data, we know that it returns D stream. I said that from when you connect to the Kafka using create direct stream or any application, you receive batches of data, and I said that batches of data are nothing but D streams, batches of data, or collection of data. So you will be getting continuously a collection of RDDs. Every 5 seconds you will be getting the RDD, and that collection of RDD is represented as D streams. So here this is our D stream. This is a D stream. So on this, first we have to decode the messages. So here we are doing, from here our actual processing of data starts here. So we are having continuous stream. This is our continuous stream. On that continuous stream, we are doing a transform. We are doing some transformation. So we have a transform higher order function. So now what is transform higher order function? So we know that on an RDD we have map higher order function. Map higher order function takes a function. That function takes each element of the RDD and transforms into something, and it will return a RDD. So we already know what does a map higher order function do. It takes a collection and transforms into another collection. It takes an RDD and transforms into another RDD based on the logic that we specify to the function that we are passing to the map higher order function. So here every batch interval. So what does the transform higher order function do? Transform higher order function is just like map is on RDD, transform is on D stream. On a D stream we have a transform higher order function. So so D stream, what is a D stream? D stream is a collection of RDDs. Each element of this D stream is an RDD. So this function takes RDD of A and transforms into RDD of B, and finally you get a D stream of B. So it is one level above it is. Just like map, it is transform. Map works on RDD collection, transform works on D stream collection. I mean D stream again you can imagine to be a collection where each element of a D stream is an RDD. So something like this, something. So if I put it in a, so we know that every batch interval we receive object. I mean we know that our Spark consumer is using Avro deserializer. The way the Avro deserializer works here is it will deserialize whatever message you have got into key value pair. The way it deserializes key is string we know, or just to put it in a much better fashion, we from the producer we have a producer, we have Avro serializer. What does this Avro serializer will do? Which will transform the message into key value pair. So key will be string. Here value is nothing but Apache log event class object. Your messages are in this fashion. Some key, random key will be there. Apache log event. So these are all your messages. An object, I mean, value will be object of this, something like this. Object 1, object 2, object 3. So this is your messages. Some key, some key. So this is how Avro will serialize. I mean, using the Avro serializer, you will create an object of this class, and these messages will be sent to Kafka. Now Spark streaming, it also has Avro deserializer. So the object will be converted into binary here and sent to Kafka. Everything will be sent to binary. So it sends this binary. From this binary, you have to get this object. That's what the Avro deserializer will do. From this binary, so these objects has to be got, which is an object of Apache log event. So internally, actually what it does is, it does not actually give you the Apache log event. It will not convert binary to Apache log event. So it will just return an object. So these objects are object of these classes. Here this object is a generic Java object. It will take that binary and it will convert into a generic Java object. That's what I took time to realize this. I was not able to work out this. I was not getting the actual messages. I was thinking that I will be getting the object of Apache log event class, but it was giving me a generic Java object. The generic Java object internally has these messages as a JSON object. The Java object internally has a JSON string kind of a, I mean each message is as a JSON string. The value is a JSON string. So it will have IP, this object will have IP, actual IP address, then it will have something like this. So that object internally has a JSON. So what we are trying to do is we are transforming this, converting from JSON to our Apache log events. We are converting our JSON to Apache. We have to do that. We have our data in the form of JSON. Each message is in the form of a JSON record. So that JSON record we will transform into Apache log event object. Apache log event object. So it will be something like this. So I will just explain that, then we will wind up the session. So we have each message as a JSON record. JSON record 2, JSON record 3, JSON record 4. Let's say this is our batch 1. In the first batch we received 4 messages. JSON 5, JSON object 6, JSON object 7, JSON object 8. In the second batch we received this message. JSON 9, JSON 10, JSON 11, JSON 12. So this is our third batch. Continuously we'll be receiving the messages. This is batch 1, this is batch 2, this is batch 3. So this is our D stream, we know that. When we connect to our Spark streaming, is receiving this D stream. D stream is a continuously getting of messages, and each messages is nothing but, I mean, for every batch interval we will be getting the messages. So on this we are calling our transform higher order function. So transform is called on dstream collection. It is a collection of RDDs. It is a collect each first element. This is element 1. Element 1 itself is a RDD. Element 2 is an second RDD. Element 3 is our third batch, which is an RDD. So transform takes an RDD. I am using the function literal here. Transform takes a function, that function takes an RDD, and whatever you want to do with the RDD, you can write the logic here. So I want to, from this RDD, take each element, JSON record 1, convert it into Apache log event object 1. So this is what we are trying to do. I'm just writing in the simplest form just for the understanding purpose. So that's where the transform higher order function comes into picture. You want to transform a complete D stream. So you have to transform individual elements of the D stream, which is an RDD. RDD itself is a collection. Again, internally you have to use the RDD API to transform each element of the RDD. So finally what you will get is, finally we'll have uh, Apache log event object 1, Apache log event object 2, Apache log event object 3, Apache log event object 4. So this RDD has been transformed to this RDD. Similarly, this RDD will be transformed to each record JSON object will be transformed to Apache log event. Apache log event. So I hope you got the idea of transform higher order function. Transform higher order function. Here a D stream has been transformed to another D stream. Just like a RDD is transformed to some other RDD, a D stream has been transformed to some other D stream. So that's what our transform higher order function does. So we are doing the same thing here. Kafka streams, as I said, it returns key value. Value is in the form of object. Value is in the form of object here. Our message is in the form of key value, offset key value. And our value is a generic Java object. That's what the Avro deserializer will return. It will return a generic deserializer. We take that RDD. We take this RDD. Now, how do I convert a JSON to a data? How do I transform? So the better way is like you take the from that RDD, take the second element of the tuple, because this is an RDD of tuple. First element is the key, second element is our actual object, which is nothing but a JSON object, convert into a string, and finally create a data frame out of. So it will just parse your JSON record and give a data frame. Each message is a JSON, right? I mean, each message of your RDD is a JSON. Convert that RDD to a data frame. So it is all about just to parse your JSON messages. Otherwise, you have to manually parse your JSON message. So after that, take each record on that data frame, get back your RDD, and create your Apache log. This is an auto-generated Avro Apache Avro class file, so that we can use this class object to do all kinds of analytics. So it takes a D stream. It takes a D stream of key values and it transforms to a D stream of Apache log event. So I hope you got the idea here. So it is a D stream of Apache log events. I mean, only few things are remaining. If I could finish it now itself, otherwise it will be very less in the next session. Yeah, I will finish it now itself. So we have transformed our uh, a generic Java object to Apache log events. From generic Java objects to Apache log events. So we have D stream of Apache log events. So from that, Apache log events has what all fields? It has a request URL field. It has IP address field. It has timestamp field. It has, using the IP address, using the request URL. Request URL is nothing but which product you are viewing. So if I want to do the analytics, how many views you have got up for a product, for a particular product. So we want to do analytics on that. For a hard disk, how many views we have got. For a laptop, how many views we have got. For women fashion, for men fashion, for some things, how many views we have got, you have to do the analytics. So we get the request URL from our Apache log event object. We get the request URL. Sometimes you may have some request URL may not exist. That's what we are checking. So how does our request URL look like? So since I myself am generating, I will show how I am generating. So in a similar fashion, it will be. So this is how our request URL will look like. Now, out of this, we have to actually get our product name. So where is our product name actually? Our product name is here. Microsoft Lumia is the product name. But the request URL contains all these things. So we will just do a split on space. We'll do a split on space, in which case this will be, when we split on, we will get this as the first element, this as the second element, and this as the third element. So from that we will get the second element. After getting the second element, again you split on forward slash. Again we split on the forward slash. So whatever is before forward slash, this will be the first element, this will be the second element, this will be the third element, and this will be our fourth element. So first you split on space, get that the URL, then you split on forward slash, then you get the product name. So that's what we are doing here. So Apache log event get request array string, split it on space, and get the, it returns an array of one. Array of one will give you the first element. So we got the product URL. From the product URI, from the product URI, we are splitting on forward slash, and we get our third element, which is the actual product name. And we just say product comma 1. Every time you receive a message, we say product comma 1, and finally we'll do a reduce by key, so that we'll get the total count for our each product. For each batch will be having that. So each batch you will have, let's say you have iPhone, you have Samsung has been purchased and viewed, again iPhone you have, again you have uh, Lumia, you have Samsung. So this is how your product will look like. After that, what we are doing is we are doing a map transformation on this, and we say iPhone comma 1, Samsung comma 1, iPhone again comma 1, Lumia comma 1, again Samsung comma 1. This is what we are doing a transformation. After doing, getting everything as Apache log events, from that Apache log event we are getting, extracting the product, then transform into a key value pair, then do a reduce by key. After doing reduce by key, what we get is iPhone as 2, Samsung as 2, and Lumia as 1. So that's how you get the count. Now this RDD we are saving to Cassandra. So in Cassandra we have a table called page views. Page views is a table in Cassandra. So that table has two columns. Table has two columns, which is page name, page, and count. So here now iPhone will become, so this we are saving. iPhone will be 2, Samsung will be 2, Lumia will be 1. Now next batch of data you get, this is batch 1. Similarly you will get batch 2, similarly you will get batch 3, similarly you will get batch 4. Every will go through this transformation, everybody will go through this transformation, and it will keep on updating. The counters will keep on incrementing. This count will be incremented. And by that you will get the, so whenever we save that, it will be incremented. So I hope you got the idea of how we are getting total views for each product. That's what we are doing. Save to Cassandra, the database name, this is the database name, this is the table name in that database, and this is our columns, page and views. So your RDD should be in the form of, if there are, if there are two columns in your table, if there are two columns in the Cassandra table, RDD should have a tuple with two elements, or a case class with two members. Your RDD should be a case class with two members, or the RDD should be having a tuple with two elements. So here if you see, this RDD after reduced by key, we get this RDD which is a tuple of two elements. If your table has more columns, those many columns should be there in your RDD as a tuple or as a case class. Each element should be either a tuple or a case class matching the number of columns in your Cassandra table. So otherwise it will fail to write the data to the Cassandra. Similarly, we are doing things for status counter. How many error code we got, how many 200 OK we got, how many 503 response we got, how many 404 error code we got. The same aggregation we are doing. So as you can see here, we are saving the data to different table. Page views are being saved to page views table. Error counts are being stored to status counter table. Similarly, we have referrer URL, whether we are getting the reference from Facebook or whether we are getting the referral from Google or Times of India or Washington Post. So those analytics we are doing. Again, those things we are doing by saving the table, saving the messages or the counts to the referrer counter. So we are saving the data to different table. So because of this reason, since there are multiple aggregations we are doing here, exactly once semantics is not possible. So exactly one semantics is possible with Cassandra only if there is a single aggregation, because in single aggregation, the table itself we can add the columns partition and offset column to the same table. But here there are different tables we are maintaining, so we have to create a separate table for offset management. Now writing to different table is not atomic operation. After writing to the table 1, then before committing the offset to the table, it can crash. So you cannot achieve exactly one semantics even if you are having the same storage for data and offset. Be- because Cassandra is not atomic. It does not support transactions, in fact. Now the last one is visit by country. So visit by country, how do we specify? Again we have to take the IP address, figure out valid IP addresses. From the IP address, split it by dot. Take your IP address, split it by dot, because your IP address will be something like this: 1 dot 2 dot 251 dot 1120 something. This is your IP address. This is how you get the messages from Kafka that a click has happened from this IP address. From this IP address, I need to get only the first two octets, because first two octets is mapped to some country code. Now how do I get the first two octets? How do I get the first two octets? So we have to just split it by dot. So that's what I am doing here. Split it by dot, you get the octets. You take the first octets. Octets is an array now. You take the first octet, then you take concatenate with the dot, get the second octet. That will be your key. Use that key and extract the data from your broadcasted object. So we have that hash map broadcasted object. Get that hash map, country code hash map. From that country code hash map, use get or else method. Pass your key and get the country name. If you don't have any country name, just return unknown country. So we get our country code. Once you get the country code, transform it into a key value pair as usual, then do a reduce by key on that, so that we get a total count for each country. Total count for each country, and finally save it to the visits by country database. So this is how you save the data to Cassandra through RDD API in Spark streaming, or you can use a data frame API is also there, but slightly it is different. I'm trying to work an example on that with structured streaming. I will showcase that example. Credit card fraud I'm working on, I will showcase that as well. But this is how you integrate or save the data to Cassandra. Once you do all these stuffs, you have processed and saved the data to Cassandra. Different tables you have saved the data. Our actual analytics is done from here. After doing this actual analytics, we are saving our offset. At the end, we are saving our to the Cassandra table. We have already seen the offset. Just like we have transform higher order function, in a similar fashion we have for each RDD higher order function. So we know that we have an RDD. RDD is a collection. On that we know we have a for each higher order function, which takes an which is called for every element of the RDD collection, and it returns unit. What do we mean by this? What do we mean is, if at all we want to save the RDD collection to an external somewhere, we use this mutability function for each. So just like we have for each on RDD, similarly there is for each RDD on D stream. If you have a D stream of type A, on that we have for each RDD, which takes a function, that function takes each element of this D stream. Each element of D stream is nothing but RDD, and it returns unit. And finally it returns it. So if at all you want to save a D stream, we use a mutability function called for each RDD. Just like transform, you can compare it with map higher order function. For each RDD, you can compare it with the for each higher order function. So this is a mutability functions. Whenever you want to save the RDD, this is immutability functions. We already know that, and that's what we are doing here. On that D stream, we call the for each higher order function. That function takes a function, and that function takes RDD as the input parameter. Each element of that D stream is an RDD, so that each element is an RDD. So we pass that RDD to our save offset. We will specify what is the database name, what is, Spark context it requires there, because we'll be dealing with the RDD, and we pass that RDD. And there we know that we are writing that RDD to a database. So that's how the things work. So I hope the the overall project was clear, and I hope how the offset management is also done is clear. And I think we have already seen the demo. So I will just show a demo once again, so that I don't remember whether the demo was recorded. I will show the demo once again here, because it will be part of the recording. So we are in Kafka. I will just start the Zookeeper server first. Server dot zookeeper dot properties. Kafka server start etc Kafka server dot properties. We'll start the Kafka server. We'll also start the schema registry. Schema registry start etc schema registry. Schema registry is also started. So let's create the topic as well. Apache log events. We'll create 3 partitions here. We'll create 3 partitions here. So we'll start sending the messages. By starting our log generator. So it will start sending the messages. Meanwhile, we'll also start our Cassandra server. So this is how we start our Cassandra. Similarly, we'll open one more terminal and we'll also start our Zeppelin server for visualization purpose. Zeppelin daemon start. So our Cassandra server is also up and running. And the tables, to create the tables, the Cassandra SQL is also there in the resource folder. Logtable.sql file, if you open that, you have to just copy these things and paste it in your Cassandra client. So we are creating this log events, key space, page views, visits by country, referrer count, Kafka offset. This is a new thing added. I will share these things. This may not exist in your virtual box. I will share these things. So this, I mean to say, so you have to create these database and tables in your Cassandra. Just copy paste this in your Cassandra SQL. So we'll go to the Cassandra SQL as well. Open one more terminal, SQL sh. So here you say describe key space. So then you say use log events key space. Again, instead of saying show tables, you say describe tables. So these tables are already created here. You can truncate everything. Truncate will remove the contents of these things. So as of now, if you say select a star from visits by country, nothing is there. If I say select star from Kafka offsets, nothing is there. So now when you start your streaming application, it will start reading the messages from your Kafka. Now we have already started. The messages are already going to Kafka now. What we'll do is we will start our streaming application as well. So come to the streaming application. So this is our log analyzer Avro Kafka streaming. Right click on that. Run Avro Kafka streaming. connecting to the Cassandra here. So it is receiving the data and writing it to Cassandra. So it should also print. I was printing the offset as well. A system a bit became a slow here. Anyway, we will check here itself. Here itself. So visits by country, as you can see, more and more data is coming. Similarly, if you see select offset. So you can see we had created three partitions for our Kafka. Hence, for each partition, what is the latest offset it has read is being written here. So it will keep on incrementing. This is how we maintain the offset. Every 5 seconds, we'll be updating this offset. So as you can see here, every 5 seconds, we are getting these many messages, and those corresponding offsets are being taken. So you can save offset anywhere. You can save it to Cassandra, you can save it to Kafka itself, you can save it to Zookeeper, you can save it to HBase, anywhere you can save it to HDFS itself, anywhere you can save it. Now if I restart my application, let me stop it. I mean, I will manually stop this. So we'll just, it is as good as saying this application has stopped. Somewhere I was printing how much offset it has. From the starting itself, we have stopped here now. So if you see it has read up till 187 offsets. So when I restart my Spark streaming application, it should start from this offset onwards. It should not start from the 0th offset. So that's how you do the offset management. So let me run this program once again. So as you can see, I'm putting the print here. So first now it read from the offset here. So this is how you maintain the offset manager. This print comes from, so this is what I'm printing. It is that print. So we are reading the offset from Cassandra. This time we got a valid offset. Otherwise nothing will be printed. Last time, very first time, nothing was printed. Now when we restarted, it started printing from here. So it means that this offset request will go to the Kafka and the messages will be read from that offset. So we can again check here, it will keep on incrementing. So now it has read up to 290 offset. So it will keep on updating every 5 seconds. So I hope you got the overall idea of how the things work, how an end-to-end pipeline works here. So that ends the end-to-end pipeline project of Spark Streaming. I hope the whole project was clear. So let's wind up the session here, and let's continue tomorrow. Tomorrow I will start with the Cassandra. How Cassandra, how to design a database in Cassandra, how an architecture of Cassandra looks like. Those things we'll see tomorrow. Thanks everybody, and have a nice day. Others, good night. Thank you.